All right, good morning, everybody, in this enormous ballroom. My name is Cassidy Barkalow. I'm here from Blue Marble Geographics. In my job, normally, I do tech support. We're a geospatial software company, so I get to answer cool questions about GIS from folks all over the place, all around the world. Today, I'm just here to talk about the need for time standards and geospatial metadata to support time-dependent positioning, though. Quick overview of how this talk's going to go. First, we'll talk about how we define locations for each other on this ever-changing planet we've got. Go over some of the reference frames involved in making those determinations. Talk about how you would transform from one datum to another, even if time is involved. How that all plays into the new National Spatial Reference System that we're getting. It has 2022 on it. It's probably coming out either later this year or next year. And then we'll wrap it on up so y'all can get on to the next talk. So y'all already know this, right? That if we need to describe a location to someone else, the first thing we need to do is agree on how we're doing that. In practice, this winds up looking like our coordinate reference systems, where you've got a grid of X and Y values you can use to specify a location, and that grid is built on top of, it's using a specific projection from a specific datum, from a specific geoid model of the planet. And we have to agree on all of those in order for the location we say to mean the same thing we want it to the person we're talking to. The challenge with that, and depending on how it's defined, it can be more or less of a challenge, is that the planet's always changing, right? We can set up this great reference system with our beautiful X and Y values and refer to things, but stuff is still happening. We all learn in school about the tectonic plates and how they move. In practice, in reality, it looks a bit more like a rotation, as you can see in this picture up here. It's an image of the velocity of movement of the North American plate over time. You can see, obviously, where the plate changes over in California. For us, it's a little bit easier. But you can see it's not just a linear shift going straight from right to left or something like that. It looks a lot more like a rotation, and it's around that sort of, you can imagine a spot in the middle of the Gulf, and that would be mathematically considered the Euler pole as the place the plates are rotating around. In addition to that pretty predictable movement, there are also the plates deform. That can be short-term changes like earthquakes, where you've got force rippling out from a location and it leaves effects behind, or long-term stuff like even subsidence, or in places that used to be covered in glaciers, the ground is actually still bouncing back from having had tons of ice on top of it. These changes are very small from one year to another even, right? Our plate moves about 2 centimeters a year, maybe about an inch. That's not a lot. Any of those deformations are also really small. And in the past, that's been fine, right? If we could kind of pretend it wasn't happening. We couldn't measure accurately enough for it to matter. But these days we can. With modern GNSS, you've got these incredible satellites where you really can measure position down to a centimeter level of accuracy. And so we do have to start thinking about, all right, well, we are moving. Those centimeters do matter now. And that ties into the more modern reference frames we wind up working with. Reference frames, some folks who are really into geodetics will argue they are not synonymous with datum, but for the purposes of this talk, we're roughly talking about datums here. Reference frames, two major kinds. There are fixed ones that don't include any information about that change over time, right? We're going to establish NAD 83 at a certain year, and then until the next iteration of it comes out, we're just going to pretend everything's the same as when it was established. And that's probably going to be good enough for most things, right? If you don't need the really high accuracy down to a centimeter level, that is fine. You can just pretend it's not moving. There are also, however, dynamic reference frames, and they include parameters for the velocity of the rotation of the plate, as well as models for the deformation that happens over time. Usually those come in a grid format. And for those dynamic reference frames, where they know that change is happening since it was first established, knowing the time your data was collected is important. You can still sort of use them and pretend everything's not moving, but to take advantage of that increased accuracy we have access to, you need to know when in addition to where. As an example of a dynamic reference frame, there's the ITRF, that's the International Terrestrial Reference Frame, and so it's a frame of reference we can all look at and use to communicate locations, and it includes models for plate movement. The origin for it is the center of the Earth. That's partly related to having been derived from these satellite measurements. We're not talking about an older system where you're creating your reference frame based on specific marks in the ground. Maybe you think of those old, the geodetic survey markers that you might see on top of a mountain. Sometimes they're in cool places, sometimes they're not. Rather than being based on those, which are inherently linked to the tectonic plate, they're literally driven into it. Instead, we're going to set the origin to be the center of the planet, since that's not so much going anywhere. These international reference frames are periodically updated. We're currently on ITRF 2020, and they can be really accurate. But again, you need to know when the data was collected to take advantage of that. All right, so we've got these new modern reference frames. We've got some older ones. What do you do if you want to go from one to the other? That sounds like it could get complicated, but we've got math for it. Datum transformations, everyone's favorite topic. You may already be familiar with some of the more basic ones, the Helmert-7 parameter, where you've got how much is it moving in X, Y, and Z? That's 3 parameters. How much is it rotating in X, Y, and Z? That's another 3. And then a scale factor as well. You can make those time dependent if you need to go to a specific date in a dynamic reference frame. That's where we get the 15 parameter Helmert transformations, where you've got each of those 7 original ones also has a velocity of change, so how much is it changing around over time to accommodate for that movement. And then there's also a 15th parameter, which is time. The way that works is, you define at a particular time. That's what those first 7 parameters are. You modify them by the second 7, depending on what that 15th time one is. And that can bring you to not just a new datum, but a new datum as it is at a specific point in time. If you want to go from one dynamic system to another one, and they're from different points in time, that's where we have our awesome National Geodetic Survey to help us out. It's an incredible government agency here in the US, and they've got this tool for horizontal time-dependent positioning. It's really amazing if you're moving from some of these time-based systems from one to another across different time spans, because it allows for transformations that do that. It does that by doing a multi-step process where you go from the first one. They kind of go through ITRF 2008, apply some extra deformation and velocity models to get to the destination datum you're going to. The picture up there, they've got 10 different grids for the United States, so that each one has a more local definition if there's interesting stuff going on geology-wise in terms of movement. Here in North Carolina, we got it pretty simple, which is great. We don't have any of this complicated stuff they've got going on out west. And this model does work internationally as well. If you ever wind up with international data, the National Geodetic Survey does have models for the rest of the world as well. They're just a more rigid tectonic plate-based system. Okay, so we've got dynamic reference frames that can incorporate time, how we can work with those if we've got data in something else. Now let's talk about the modernization of our National Spatial Reference System. This is a really cool project from those folks at the National Geodetic Survey that they're working on, because our current National Spatial Reference System is a bit old. It is fixed rather than dynamic, meaning that it makes no allowance for the changes that are constantly happening. It just kind of pretends they don't happen. The new spatial reference system will be dynamic, so it'll include those models for velocity and deformation. In the process, they're also fixing some long-standing errors in it. That diagram up there shows a bit. The place where NAD 83 considers to be the center of the Earth is actually off by a little over 2 meters, which on the scale of the Earth, again, isn't a whole lot, but it does come into play, especially if you're doing any of the vertical measurements out there. Those will be pretty different in the new reference system. They will be publishing new realizations of it every 5 years. It'll line up with those international terrestrial reference frames. We can get on the same page as a lot of the other countries in the world that are already doing it. Side note, they're splitting into 4 reference frames rather than 3. The Caribbean will no longer be in the same reference system as us. They'll get their own datum. They've got their own stuff going on down there. This is really cool, right? We're getting all these more accurate significantly more accurate reference frames that can let us all take better advantage of these modern technology. We're getting new vertical and horizontal datums that include models for movement and change. There'll be a new geoid model of the planet that's more accurate, underlying it all. We're getting new state plane coordinate systems that use all of that. And you need time to take advantage of that increased accuracy. The real benefits of these dynamic reference frames only come into play if you know when your data is from. And so that's why we really need to start tracking that in our metadata. Right now, there isn't a unified standard for saving time information in geospatial metadata, especially in the metadata formats that are machine readable, right? Some of those formats can include time, some can't. For example, if you've got a PRJ with your projection, there is nowhere to even put time in that if you wanted to specify, okay, well, what day or what year was this from in this new National Spatial Reference System? You just can't. It would have to go, in a separate file with other metadata that you might even have to enter manually. For other formats, the ones where maybe you've got your projection information in the header, it varies how and whether they record it, and that could cause issues in the future, right? Whether it's human-readable metadata or not, this is information that could be important. Who here still occasionally or frequently uses data that's at least 10 years old? All right, yeah, we got a couple people. 20 years old? Every once in a while? All right. So it's safe to assume that any data you're collecting in the next year or two could still be in use in the future. Folks in the future might want to be really accurate with it. They'll appreciate knowing the day that it was collected. So for now, while we're waiting for official standards to come out for metadata and how we can actually keep that information, in a way that the computer will just pick it up on its own, you don't even need to think about it, same as most of the time now, please find some way to list time in the metadata for your data. That might mean, if you're still working with shapefiles, you got a PRJ, you've probably also got an XML, and you can make sure it's in a text field in there. If you can even at least include the year, that's great. Even better if you can have the whole date. And try and keep the month and day unambiguous. Here in the US, we love our month, day, year format. Today is March 20th, 2025. But in other parts of the world, they don't do that. That's not as easy for computers, which track time in all kinds of ways. So if you're writing it out by hand just somewhere so that a future person could at least hypothetically find it, try and keep that unambiguous. Maybe year, month, day is a good way to go. All in all, improving technology lets us track location more accurately than ever. We can have centimeter-level precision with our measurements. But because the planet is always changing, if there isn't care taken to track not just what kind of datum was being used, what kind of equipment was being used, but also when the data was collected, we can lose that accuracy over time, which would be a shame if we're going out of our way to get it in the first place. So please include time information in your metadata, and just keep an eye out for the role of time in metadata standards as they're updated. If you're collecting data and giving it to somebody else, make sure your timestamps aren't getting lost or overwritten with a file creation date or something like that. There we go. If anybody has any questions, I'm happy to answer them. Thank you all for listening. Yeah, back there.
Just out of curiosity, why hasn't time been a factor with this? Why haven't they been keeping a record?
Yeah, so the question was, why hasn't there been a standard for keeping time like this in the past? And it's because largely it wasn't an important separate parameter. And historically, datums would have some kind of a year listed with them, where you'll hear like NAD 27, NAD 83. For NAD 27, all you really need to know is that it's NAD 27. We weren't accurate enough for it to matter whether that data was collected in 1934 or 1952. It was going to be about as accurate either way. So there wasn't really a need for an additional place to put in, oh, no, it was actually February 27th, 1954 that this data was from, because the accuracy just wasn't there. Any other questions? All right, well, if you come up with any later, you're welcome to stop by the Blue Marble Geographics booth. We're over in the exhibit hall. Happy to talk about geodetics and metadata, everyone's favorite topics. Thanks.